So you're running a 3D reconstruction model on a live video feed. Everything looks perfect for the first few seconds, but around, say, frame 800, the trajectory just drifts into this wall of noise, your GPU spikes, and the system throws a fatal out-of-memory error.
Yeah, it is a nightmare.
Right. If you are an ML engineer building long-context AI applications, you know this pain entirely too well. So today, we are doing a deep dive into the paper R3, 3D Reconstruction via Relative Regression by researchers from the University of Michigan, Westlake University, and NVIDIA.
It is such a fascinating approach.
It really is.
Yeah.
Basically, R3 fundamentally shifts 3D geometry foundation models away from predicting global coordinate frames. By employing a lightweight MLP on a DA3 backbone, it predicts pairwise relative poses along with decoupled rotation and translation confidences.
Which is the real secret sauce there.
Exactly. And this allows for causal bounded memory streaming that scales to literally thousands of frames at over 30 frames per second without those OMers or catastrophic drift. And it does all this using a highly efficient 372 million parameter model.
Yeah, I mean, it directly addresses a structural flaw in how the whole industry approaches feed-forward 3D reconstruction right now.
Right.
To really grasp what R3 accomplishes, we need to step back and examine the exact bottleneck that's just, choking current state-of-the-art models.
Like DUST3R and those guys.
Yeah, exactly. Recent systems, so architectures like DUST3R, VGGT, DA3, or TIT3, they have made incredible strides. Like, they can take a handful of images and recover depth maps and camera poses in a single forward pass.
Which is amazing.
It is. But the issue is that their architectures rely really heavily on absolute pose regression.
Meaning they force the neural network to map everything back to one arbitrary origin.
Right. They map every incoming view to a single temporal origin point.
And that origin is usually what, just the very first camera frame the system sees?
Yeah, usually the first frame, or sometimes this learned canonical coordinate space. And, for a short offline clip where you just feed the network 10 or 20 frames all at once, mapping everything back to frame 0 works fine.
Because the network has the capacity for that.
Exactly. It can hold that small spatial relationship in its weights and output a clean 3D point cloud. But the architecture totally breaks down the moment you transition to long videos or like open-ended streaming.
Because in streaming, you don't even know the sequence length.
Right. If a network is forced to maintain a consistent global frame as thousands of new views just keep arriving, the translation magnitudes, the actual numerical distances from that original origin point, they just grow mathematically unbounded.
Right, because if frame 10,000 is literally miles away from frame 1, you're asking the neural network to output these massive numerical coordinates, right?
Exactly.
While simultaneously maintaining like millimeter level precision for the local geometry right in front of the camera. The network's weights simply don't have the capacity for that kind of dynamic range.
They really don't. The term for this in the literature is the coordinate choice problem. The network's future poses become heavily biased toward the coordinate frame it initialized with from those early observations.
Even with models that try to fix this, right? Like Pi3
Yeah, even Pi3 It tries to mitigate the issue by incorporating relative pose supervision during training, but it still ultimately outputs a set of global poses tied to one coordinate system.
So it's still forcing the model to represent the entire trajectory geometry in a single pass.
Precisely. And as the camera moves further from the origin, the regression task eventually just drifts way out of the numerical distribution the model saw during training. The predictions just degrade into pure noise.
So it's like a GPS analogy, right? Global regression is like navigating this massive moving crowd by giving everyone absolute GPS coordinates based on a starting point 5 miles away.
That's a great way to put it.
If there is even a fractional error in the signal, those errors compound massively over time. Soon, nobody knows exactly where they are relative to the person standing right next to them because they're just too busy calculating their distance from a point they can't even see anymore.
Yeah, exactly.
Whereas relative regression, which R3 proposes, abandons that global map entirely. It just says, take 2 steps left from your current position and rotate 45 degrees. The scale of the prediction depends entirely on the physical baseline between 2 adjacent frames, not the whole trajectory.
Right, because a $1 frame sequence inherently contains this massive matrix of pairwise constraints, like $1 potential relative constraints, rather than just $1 absolute poses.
Wow, yeah.
So R3 operates on the premise that a feed-forward neural network should really only be tasked with learning these local relations between views, assembling those local relations into a global trajectory. That's treated as an entirely separate downstream task.
Okay, wait, let me push back on this a bit.
Sure.
If you only have relative steps, like just local edges connecting frame A to frame B and frame B to frame C, how do you avoid a catastrophic game of telephone when assembling the final map?
The telephone game's a huge risk, yeah.
Because if frame A miscalculates its relative distance to B, and then B miscalculates its distance to C, by the time you chain 1,000 frames together, the accumulated error should make the global trajectory completely unrecognizable, right?
Absolutely. Blindly chaining pairwise predictions definitely results in that telephone game, because pairs of frames in a real-world video differ wildly.
Right, you get motion blur or whatever.
Exactly. You have varying degrees of visibility, textureless surfaces, motion blur, sudden changes in baseline distance. If a model just regresses relative poses for all possible pairs and blindly hands them off to an aggregation algorithm, the algorithm has no signal indicating which local steps are actually trustworthy.
So how does R3 fix that?
To prevent that accumulation of error, R3 introduces something called decoupled confidence modeling.
Okay, let's unpack this. The architecture uses a DA3 geometry backbone, right? Which processes the images into latent geometric representations.
Yep.
And they keep that backbone frozen and just slap a shared lightweight multi-layer perceptron or MLP on top.
It's very lightweight.
So when this MLP processes the camera tokens from two different frames, it outputs the relative rotation and relative translation. But alongside those standard geometric outputs, it generates two distinct scalar values.
Yes.
One confidence score specifically for rotation and one specifically for translation.
And that decision to split those confidence metrics is a huge divergence from prior methods. It's critical.
Why is splitting them so important?
Because in visual 3D geometry, rotation and translation fail under entirely different conditions. Like, translation estimation is notoriously sensitive to weak geometric cues.
Like what kind of cues?
Like if a camera moves through a totally featureless hallway, or if there's a lack of parallax, or maybe a really large object just moves across the foreground, your translation estimate can become completely unreliable.
The rotation is different.
Exactly. Rotation, conversely, can often remain totally locked in. You can determine your orientation from distant vanishing points or background features, even if your forward movement is completely ambiguous.
Ah, I see. So if the network only output a single unified confidence score for the entire relative pose, it would be forced into a mathematical compromise.
Right.
It would have to penalize a highly accurate rotation estimate just because the translation data was noisy. Or worse, it might assign a high confidence to a faulty translation because the rotation was perfectly clear.
Exactly. By decoupling them, any downstream algorithm using this data knows exactly which specific component of the geometric step it can actually trust.
That makes so much sense.
And the really cool part is that the decoupled confidence isn't merely an uncertainty metric just tacked on at the end of the pipeline. It functions as a unified primitive that actively shapes how the network learns.
Wait, how does it shape the learning?
The training process relies on a confidence-weighted L1 residual loss function.
Okay, what does that mean in practice?
So the actual geometric error of the pose prediction is multiplied by the predicted confidence score. And then a logarithmic regularizer, specifically the negative log of the confidence, is subtracted from that product.
Oh, wow. Okay, so the tension built into that specific equation creates a really strict optimization boundary.
Yes, exactly.
Because if the network outputs a wildly incorrect relative pose for a pair of frames and simultaneously predicts a high confidence score for that pair, multiplying the large error by the high confidence just results in a massive penalty from the optimizer.
You got it. The network quickly learns that to minimize its loss on difficult frame pairs, it needs to shrink that confidence score down.
But wait, what stops it from just predicting zero confidence everywhere? Like, just to avoid the error penalty entirely?
That is where the negative log regularizer comes in. It prevents the network from taking the easy way out. If it predicted zero confidence, the negative log of $2 term would spike toward infinity, incurring a massive loss anyway.
Oh, that is clever.
Yeah, the network is forced into this optimization bottleneck. It literally must selectively downweight unreliable pairs just enough to mitigate the geometric error penalty, but maintain high confidence wherever the geometric signal is actually clear.
I have to challenge this a bit, though. Is this just a clever loss-weighting trick for smoother gradient descent, or does it translate to a genuinely reliable metric for real-world geometry?
It translates remarkably well to the real world.
Really? Like, when the model is actually deployed on a drone and outputs a translation confidence of 0.1 for a pair of frames versus 0.9 for another, does that 0.1 definitively mean the prediction is unusable?
The empirical validation in the paper confirms the correlation is incredibly direct. If you look at Figure 8 in their study, they plot image pairs from the ScanNet test scenes, binning them strictly by their predicted confidence scores.
And what does the plot look like?
The relationship is entirely monotonic. A high predicted confidence score maps flawlessly to a very low mean pose error with a super tight variance.
Wow.
And conversely, pairs that the network assigned low confidence scores to exhibit massive real-world pose errors and huge variances. So the architecture isn't just smoothing its gradients, it has genuinely learned to quantify its own geometric uncertainty based directly on the visual input.
Which provides the exact mechanism needed to solve that out-of-memory problem during live, open-ended streaming.
Exactly.
Because if the system possesses a verified signal for geometric reliability, it no longer needs to retain every single frame in its memory to build the trajectory. It can afford to be highly selective.
Right, it doesn't need to hoard data.
So R3 manages continuous video feeds by maintaining what they call an active context, or a keyframe bank. And it strictly bounds memory usage by capping this bank. Like, for instance, allowing a maximum of only 100 frames at any given time.
Yep. But the challenge then becomes the selection criteria. Streaming a 10,000 frame video through a 100 frame bottleneck requires rigorous admission and eviction policies.
You can't just let any frame in.
Right. R3 does not automatically admit new frames into the keyframe bank. When a new frame is processed, the system measures the cosine similarity between the new frame's pre-attention backbone token and the tokens already residing in the bank.
Okay, so checking how similar the features are.
Exactly. If that cosine similarity exceeds a specific threshold, they identified 0.98 as the optimal limit. The system determines the new frame offers no novel geometric information and just rejects it.
It's basically like a ruthless nightclub bouncer.
Yeah, pretty much.
Like if a new frame walks up to the door and its geometric features look 98% identical to a frame already inside the active context, the bouncer denies entry because the frame is redundant.
Spot on.
But if the active context is completely full at 100 frames and a new, highly distinct frame arrives, like perhaps the camera just turned a corner into a new room, the bouncer has to evict someone to make room, right?
Right, someone's got to go.
So R3 handles this by calculating a utility score for every frame currently in the bank and evicting the one with the lowest score.
And that utility score is a really smart composite metric. It evaluates how redundant a frame's features are compared to its neighbors in the bank. But critically, it also factors in that pose head confidence we just discussed.
Oh, so the confidence comes back into play here.
Exactly. If a frame in the bank has weak pairwise confidence scores connecting it to the rest of the active context, its utility plummets and it gets evicted. This mechanism ensures the 100 frames retained in GPU memory are structurally vital and highly reliable.
Brilliant.
But the admission process actually includes an even more aggressive filter, which they call the outlier gate.
Because redundant frames just waste memory, but outlier frames actively destroy trajectories, right?
Yep. Think about it. A drone camera might suddenly capture heavy motion blur from a sudden gust of wind, or a person might walk directly in front of the lens, occluding the entire scene.
Right, and in a traditional global regression model, the features from that heavily occluded or blurred frame are permanently embedded into the global state.
Exactly, which corrupts the coordinate frame and introduces that catastrophic drift we talked about earlier.
So how does the outlier gate stop that?
R3 leverages its confidence metric again. If a newly arriving frame generates a low average confidence score when paired against the frames already in the active context, the outlier gate triggers. R3 immediately invalidates that frame's KV cache entries.
Wow, just instantly.
Instantly, it purges the bad data in a single online pass.
Just for context for you listening, vision models use a key value cache, or KV cache, to allow the attention mechanism to reference past frames without constantly recomputing them from scratch.
Right.
So if a toxic frame is allowed to store its keys and values in that cache, every subsequent frame will attend to that noisy data, essentially polluting the entire geometric representation.
It poisons the well.
Exactly. By bouncing the frame's KV cache entirely at the door, R3 ensures the attention mechanism remains pristine for future frames.
And the efficiency of that single pass rejection is profound. Compare this to prior robust streaming models like robust VGGT.
How do they handle it?
Well, those architectures require a multi-pass offline detection stage. They have to process chunks of the sequence, analyze the trajectory for anomalies, identify the distracting frames after the fact, and then completely reprocess the data.
That sounds incredibly slow.
It is. R3 identifies the compromised geometry purely through its confidence prediction at the exact moment of intake, drops the cache, and just continues streaming without interruption.
All of this architectural discipline, like the relative local steps, the decoupled confidence, the strict bounded memory, it culminates in highly disruptive performance benchmarks. I mean, we are analyzing a model with only 372 million parameters, which the researchers trained on just 6 48-gigabyte GPUs.
Which is almost nothing in today's landscape.
Right. That is a fraction of the compute required for recent billion-parameter foundation models in the 3D reconstruction space.
And when benchmarked against those massive architectures, including models like Stream VGGT, CUT3R, and TT23R, the long sequence scalability of R3 becomes immediately apparent.
The numbers are wild.
Yeah. The researchers tested these models on 1,000 frame sequences from the 7 scenes and ScanIt datasets. The global regression baselines predictably failed.
Right. They either hit out of memory limits as their active contexts swelled, or their trajectories collapsed into meaningless noise due to out-of-distribution drift.
Yep. But R3 maintained a stable, highly accurate trajectory at over 30 frames per second indefinitely.
The DL3DV benchmark results really highlight the disparity, too. That benchmark rigorously tests camera trajectory accuracy over long, complex, real-world sequences. R3 actually secured the lowest absolute trajectory error on 24 out of the 25 tested scenes.
That's a 96% win rate against models way bigger than it.
Yeah, it isn't merely surviving these long sequences by dropping data. It is extracting a higher quality geometric signal than models 3 times its parameter count.
Yeah.
And crucially, its memory footprint plateaus the moment the keyframe bank hits its 100-frame limit.
Which makes it completely viable for edge devices and robotics, while the baseline models just consume memory linearly until the hardware crashes.
Here's where it gets really interesting, though. There is a final structural advantage to this architecture that bridges the gap between real-time streaming and offline processing.
Yes, the full context switch.
Right. R3 was purpose-built as a causal architecture for live bounded memory streaming, meaning the model can only look backward at the active context. It cannot see the future frames.
Right, because it's meant to be live.
But if the use case changes, say you have an entire pre-recorded video file, and your goal is the highest fidelity 3D reconstruction possible without real-time constraints, R3 includes a full context switch.
And it is so elegant because you don't need to load a separate offline model or retrain the weights.
Right, because the core output of the neural network is exclusively pairwise relative poses and their associated confidences. You simply disable the causal attention mask during inference.
Exactly. Suddenly, the DA3 backbone can see the entire sequence simultaneously. You extract the camera tokens for all frames and query the lightweight MLP on every possible pair to generate this massive web of relative connections.
And the aggregation step is where the decoupled confidence truly shines in that offline mode.
Oh, absolutely. Because instead of forcing the neural network to output the final global map itself, you pass all those relative poses to a classical pose graph optimization solver. And you use the network's predicted confidence scores as the explicit edge weights in that graph.
I love this part. The classical solver is essentially mapping out nodes and springs, right? Where the frames are nodes and the relative poses are the springs connecting them.
Yes, perfect analogy.
And the confidence score basically dictates the stiffness of the spring. You are telling the solver, align this entire trajectory, but when 2 relative predictions contradict each other, trust the rigid spring with the 0.9 confidence and let the loose spring with the 0.1 confidence stretch or break.
Exactly. By combining the feed-forward feature extraction of a foundation model with the mathematical rigor of classical graph optimization, R3 achieves near-perfect global alignment.
It's just so robust.
It really is. The exact same confidence signal is utilized 3 completely different ways. It weights the loss function during training, it manages the KB cache eviction during live streaming, and it serves as the definitive edge weight for offline graph refinement.
So what does this all mean?
Well, I think for ML engineers looking at the future of 3D spatial intelligence, the core takeaway is about assigning the right tasks to the right systems.
Right. Forcing a neural network to memorize a global map and output absolute coordinates is just fighting the fundamental math of neural capacity.
Neural networks are exceptional at extracting local geometric features and estimating their own uncertainty.
While classical graph algorithms are exceptional at globally aligning constrained edges.
Exactly. By predicting relative poses with decoupled confidence, R3 successfully isolates those two strengths.
And it forces us to reconsider how we approach long-context spatial and temporal reasoning in entirely different domains, honestly.
Oh, definitely. If decoupled confidence operates this effectively as a unified primitive for 3D alignment completely neutralizing the memory limits and out-of-distribution drift that destroy long sequences, this paradigm likely has massive applications elsewhere.
Yeah, consider long-horizon autoregressive video generation, where models eventually devolve into noisy structural sludge because they lose their temporal grounding.
Or robotic manipulation models that just forget their spatial context during multi-step, open-ended tasks.
Right. If those systems stopped trying to predict absolute global states and instead predicted relative state changes bound by strict, learned confidence metrics, the context windows could theoretically scale infinitely.
It's a huge shift in thinking.
It really is. Well, that is all for this deep dive into the R3 paper. We highly encourage you to pull up the original research to review the mathematical proofs and the trajectory benchmarks for yourself. Thanks for joining us on AI Paper Slop, and we will catch you next time.